In 2008, a crisis hit southern China that most of the world never noticed. A rare ice storm blanketed Hunan, Hubei, and Guizhou provinces. Transmission lines froze, towers collapsed. More than 10 million households lost power in below-zero temperatures, some of them for nearly 3 weeks. The storm did not destroy the power system. It only exposed something that had been true for a long time. China's electricity was in the wrong place. Coal was in the northwest. Hydropower was in the southwest. The population was on the eastern coast. Moving power from where it was generated to where it was consumed meant crossing 3,000 kilometers of mountains, plains, and rivers. And the transmission network China had at the time was never designed for distances like that. Today, China operates an ultra-high voltage transmission network that spans the entire country. It carries wind power from Xinjiang to Jiangsu, hydropower from Yunnan to Guangdong, solar power from Inner Mongolia to Beijing. The longest single line runs more than 3,300 kilometers, longer than the distance from London to Cairo. Across that distance, the network loses less than 1.5% of the electricity it carries. The United States high-voltage transmission grid loses between 6 and 8% on comparable routes. The same unit of electricity, leaving a power plant. On China's network, 98.5% arrives at the destination. On the American grid, the loss over equivalent distances amounts to nearly 1 full month of generation output per year. This is not a marginal efficiency improvement. This is a categorically different technology. To understand why this is so difficult, you need to understand the physics of voltage and distance. Electricity generates heat as it moves through a wire. The lower the voltage, the more heat it produces, and the more power is lost. This is why all long-distance transmission requires stepping up the voltage. Higher voltage means more power through the same wire, with less heat loss. Standard high-voltage transmission lines operate at 500 kilovolts. That has been the global industry benchmark for decades. China's ultra-high voltage lines operate at 1,000 kilovolts AC, or 800 kilovolts DC. 1,000 kilovolts. This is not a modest improvement over 500. This is a physically different operating regime. At these voltage levels, the air itself begins to conduct electricity. Insulation materials behave differently. The electromagnetic field intensity around the conductors cannot be fully predicted by existing engineering theory. Before China built its first UHV line, nobody had operated at this voltage level at commercial scale. There was no equipment to buy, no standard to reference, no engineering manual to consult. The man who pushed this into existence was named Liu Zhenya. In the 1990s, he was an engineer at State Grid Corporation of China, not a bureaucrat, not a scientist, an engineer who worked in substations and understood how power grids actually function. He saw, even then, the structural contradiction in China's electricity map. Resources in the west, demand in the east, 3,000 kilometers in between. He ran a calculation. If China tried to transmit all of its developable Western power resources using the existing 500 kilovolt network, how many lines would need to be built? How many land corridors consumed? How much steel and copper used? The numbers told him the path was impossible. Western resources could not be economically delivered to Eastern demand with existing technology. He began pushing an idea that almost nobody supported at the time: skip 700 kilovolts entirely. Go directly to 1,000. In 2004, CIGRE, the International Council on Large Electric Systems, the highest academic body in power engineering, published a report stating explicitly that ultra-high voltage transmission faced fundamental technical barriers and was not commercially viable. Liu Zhenya's team kept going. On January 6, 2009, China's first ultra-high voltage AC transmission line entered commercial operation. The Jindongnan to Nanyang to Jingmen line, 654 kilometers. Operating voltage, 1,000 kilovolts. The insulation breakdown that CIGRE's report had predicted did not happen. The uncontrolled corona discharge did not happen. None of the failures that international experts had considered inevitable at this voltage level occurred. It simply worked. In the 15 years that followed, China built 33 ultra-high voltage lines, totaling more than 40,000 kilometers. Among them, the world's first plus or minus 800 kilovolt DC ultra-high voltage line, running directly from hydropower stations in Hunan to load centers in Guangdong, 1,373 kilometers, with a single line transmission capacity of 6.4 gigawatts. That is the equivalent output of 6 large nuclear power plants carried by one wire. No other country has built one. The West does not have ultra-high voltage transmission, not because it was never considered, but because before China proved it worked, nobody could confirm it was possible. America's transmission infrastructure was largely built in the mid-20th century. Large portions of the backbone grid still operate at voltage levels designed 60 years ago. A 2023 U.S. Department of Energy report noted that the electricity lost annually to transmission inefficiency and grid aging in the United States is enough to power the entire state of Texas for 2 years. Europe's situation is somewhat better, but Europe does not need 3,000-kilometer transmission distances. The geography does not require UHV. The countries that genuinely need it are those where energy resources and population centers are separated by continental distances. China was the first. Now Brazil is building. India is in negotiations. Saudi Arabia's megagrid project is evaluating Chinese technical standards. Liu Zhenya, after retiring, published a book proposing that UHV technology could connect the world's renewable energy resources into a single global grid: Saharan solar to Europe, Siberian wind to East Asia, Brazilian hydropower to North America. In 2015, that idea was considered an engineer's fantasy. Before 2009, 1,000 kilovolt transmission was considered a fantasy too. In 2008, the 10 million households who lost power in that ice storm spent nearly 3 weeks by candlelight. What the blackout left behind was not only a memory of infrastructure vulnerability, it was a question that could not be avoided. If China could not solve the structural contradiction of its electricity map with existing technology, it would need to build technology that did not yet exist. They built it. The network now transmits more than 2 trillion kilowatt-hours of electricity per year. Every unit generated 3,000 kilometers away, arriving at its destination having lost less than 1.5% of itself along the way. You cannot see this infrastructure. It runs underground, or suspended above valleys you will never pass through. But if you turn on a light in Shanghai tonight, some of what illuminates the room began as wind in Xinjiang. If this shifted how you think about energy infrastructure, the like button is the fastest signal you can send. And if you think this same logic is already running in another industry, write it in the comments. We read every one.